All right, I guess we'll get started. Ready? So I am very happy to introduce Maura McLaughlin. She is joining us from West Virginia University. She is the chair there now of their department. She's also the Eberly Family Distinguished Professor of Physics and Astronomy. Or is it astrophysics? Astronomy. She's the co-director of NANOGrav. She is the co-discoverer of fast radio bursts. She is the winner of the Shaw Prize, which is called the Nobel of the East. Maura started off, she did her undergraduate at Penn State, did her grad time at Cornell. Then she went to Jodrell Bank in the UK, and then started in West Virginia in 2006, and has been there since. One quick note, we still have one slot for dinner. It's at Leaf at 6:45. If you're interested, let me or Mitch know. So I think, Maura, if you're ready, I'll be very happy to hear from Maura about using pulsars to detect gravitational waves.
Hey everybody, can you hear me? Do I need to move this up or down? Can you hear me in the back? Okay, great. Yeah, it's really nice to see all of you. I've enjoyed my day here so far. Boulder is beautiful, and there's so many astronomers here doing lots of really interesting things. Yeah, so as Jeremy said, I'm going to tell you about the work of the NANOGrav collaboration. So NANOGrav stands for North American Nanohertz Observatory for Gravitational Waves. And this little cartoon sums up what it is we're trying to do. We're using large radio telescopes to observe radio pulsars. And we're timing those pulsars to search for very small perturbations due to very low frequency gravitational waves. And we think the most likely source of those waves are supermassive black hole pairs at the cores of galaxy mergers. So this is the big picture of our project. And if you want to sleep for the rest of the colloquium, this is our result, which I'm going to tell you about. So back in June of last year, we announced the big result, which was the culmination of 15 years of observing. So we announced results on our 15-year pulsar timing dataset, in which, for the first time ever, we saw this very special correlation between the arrival times of the pulsars versus their angular separation on the sky. This black dotted line is what's predicted by general relativity, and these blue points are our measurements. So I'll tell you all about how we time the pulsars to get data like this, how we do this correlation analysis, what it means, and then what the next steps are. This was a pretty fun announcement. I didn't think it would get a lot of popular attention, like it's kind of an esoteric thing, but there were lots of really great news articles, stuff like the cosmos is thrumming with gravitational waves, or space-time churns like a choppy sea, and I think this was my favorite. Scientists found ripples in space and time, and you have to buy groceries. So this was fun, but it's really just the beginning, as you will see. Let me just tell you a little bit about the people that I work with on this project. So NANOGrav was formed in 2008. We're over 200 students and scientists, mostly at institutions in the United States and Canada, hence the North American. We're funded by the National Science Foundation as a Physics Frontier Center, and we've been funded as a PFC since 2015, so we're on our second round of PFC funding. We have a website, of course. We've recently upgraded it with lots of nice images and explanations of our science, so feel free to go there to learn more about us. NANOGrav is also a member of a broader international collaboration called the International Pulsar Timing Array. So that's a consortium of consortia, so it's NANOGrav, and then groups in Europe, India, Australia, and South Africa who are doing similar things to us. And the idea is that we combine all of the data from all these different collaborations worldwide to do the same experiment I'm going to tell you about today. Okay, so super big picture, why do we want to detect low frequency gravitational waves? So our primary motivation, or at least my primary motivation, is really understanding some very fundamental things about the universe, like how galaxies have grown and evolved with cosmic time, right? So this is the standard picture of hierarchical galaxy formation. So galaxies start off small and irregularly shaped, and they grow bigger and more regularly shaped through mergers, right? So we think that galaxy mergers are a very important part of the history of the universe. We can, of course, identify merging galaxies electromagnetically when they have separations like this. but when they're in the very final stage of a merger, when the two black holes are separated by subparsec scales, we can't tell, right, if a galaxy we observe electromagnetically is the product of a merger or not, right? We can't tell looking at this galaxy that it has two black holes at the core electromagnetically. And there's lots of really interesting astrophysics. You may have heard of the final parsec problem or the last parsec problem. So like, what are the astrophysical things that bring these supermassive black hole binaries together to be close enough so that gravitational wave emission can take over and force their merger into a single supermassive black hole? What are the roles of, say, accretion, stellar scattering? Are the orbits eccentric? Are they circular? There's lots of things we don't understand about this very fundamental process. And of course, the only way we can study these black holes with these close separations is through gravitational waves. I'm sure you've all heard of gravitational waves, right? So these are predicted by general relativity. Objects in binary systems emit these waves. Very massive black holes emit prodigious amounts of these gravitational waves. We can detect gravitational waves from individual supermassive black hole binaries. We can also detect a background, the combination of all of the waves from all of these merging supermassive black holes throughout the universe. So LIGO has detected gravitational waves, as you know. So there's something like 100 compact binary mergers that have been detected with LIGO, right? And these things have masses from, say, a couple times the mass of the sun to 100 times the mass of the sun. So these are neutron star and black hole mergers. And it helps just to kind of look, I think, at how LIGO works before moving on to the Pulsar experiment, because it's a nice analogy. So this is a picture of one of the LIGO interferometers, and you can see, right, it's got two arms that are perpendicular to each other. Lasers travel up and down these arms, and an interference pattern is measured at the detector. And when a gravitational wave passes through the LIGO detector, one arm, oh, I want to start my little movie. There we go. Okay. One arm gets longer, and the other arm gets shorter, and hence the lasers travel different path lengths when a gravitational wave is moving through the detector than they do when it's not, right? And the reason the LIGO arms are at 90 degrees is because of this quadrupolar perturbation pattern of gravitational waves. So if a gravitational wave would travel through the screen and there was a ring of test particles, it would cause the distances between the particles to move in this very special way. So the circle kind of gets like scrunched and squeezed and scrunched and squeezed. And so that's why the LIGO arms are at 90 degrees, because you're going to get the maximum possible perturbation in the arms, right? One will get stretched and the other will get squeezed like this. Okay, that's how LIGO works. We want to do a similar thing with our Pulsar experiment. However, we want to be sensitive to much lower frequency waves, which means we need a much, much bigger detector than LIGO, right? And so we do that by constructing a natural galactic scale detector using radio pulsars. So radio pulsars are neutron stars. They're born in supernova explosions. You can study them across the electromagnetic spectrum, but everything I'll talk about today is done with radio telescopes. Here's the standard. I can't have a colloquium about pulsars without just showing the standard little pulsar movie. You can kind of hear that, I think. A little blip every rotation. So here's a neutron star. Pulsars have high magnetic fields, so they have a north and south magnetic pole. Particles are accelerated along those north and south poles, and then, of course, every time the pulsar spins, we detect a blip, a radio blip of emission. So there are about 5,000 pulsars known right now. We cannot use most of them for our experiment. We can only use a very special subset of those pulsars called millisecond pulsars. So these millisecond pulsars spin with very short millisecond periods, so like 1 to 10 milliseconds. They're recycled pulsars, so they're very old pulsars. They've been spun up to very short periods through the accretion of matter and angular momentum from a companion star. There's about 350 of those within our galaxy, and as you'll see, we're timing 70 of them for our experiment. Not all of them are stable enough, nearby enough, bright enough to be used for gravitational wave detection. Okay, so our experiment is a PTA experiment, or a pulsar timing array experiment. just what it sounds like. We observe an array of these millisecond pulsars distributed across the sky, and we search for correlated changes in the arrival times of pulses from this array of pulsars. This is a nice little cartoon which shows the basic idea. There's the Earth, there's some pulsars. So just like LIGO has these two 4-kilometer arms, our experiment has 70 arms that are thousands of light years long. LIGO has 40-kilogram test masses. Our test masses are about 1.5 to 2 times the mass of the sun, but it's the same idea. We're searching for changes in the distance between the pulsars and the Earth due to gravitational waves passing between the pulsars and the Earth. One subtlety that's a little different between the LIGO and the Pulsar experiment is that when a gravitational wave passes through the LIGO detector, it will stretch and squeeze the whole arm. The wavelength is bigger than the detector. For our experiment, we actually have many gravitational wave wavelengths in between the Earth and the pulsar. So we have a pulsar term perturbation and an Earth term perturbation, and they'll actually look different. So for a single gravitational wave source, the perturbation at the pulsar and the perturbation at the Earth will be different because the gravitational wave will hit those two objects at different times in its evolution. So there's basically 2 terms to account for in the perturbation. If that sounds confusing, we'll talk about this a little more later on. And so we search for very specific angular correlations in arrival times. So this little cartoon here generally shows the kind of correlations we expect. So if 2 pulsars are in the same direction, they're going to have correlated changes in their arrival times. If they're separated, by 90 degrees, they're going to have anti-correlated perturbations, right? Just because of that little cartoon we watched earlier of how gravitational waves have this quadrupolar effect. And if they're separated by 180 degrees, we expect a positive correlation again, right? So this is the general kind of signature we're looking for in our data. If you do the math, it looks a little more complicated. So this is something called the Hellings and Downs curve. And this is the correlation you expect in pulsar arrival times if you average over an isotropic distribution of gravitational wave sources and an isotropic distribution of pulsars, and you assume general relativity is correct. So we have a peak at 0 degrees. So this is the positive correlation for pulsars in the same direction, a dip around 90, and a positive correlation at 180 again. So this is the signature that we're looking for in our pulsar timing data. One kind of fun thing is if you look here, this is 0.5, not 1. We would never expect perfect correlation because the pulsar terms, and one really important thing that I should have pointed out, this is for a stochastic background. So this is for like a whole bunch of gravitational wave sources, right? I guess I did say that, an isotropic distribution, but purely stochastic. So this is the superposition of all of the signals from all of the supermassive black hole binaries in the universe. And the pulsar terms will be all uncorrelated, right? They're all at different distances. They're all going to be affected in different ways at any one time, right? So the only thing we're seeing here is the Earth term of the correlation. So our detection is really the effect of gravitational waves on the Earth. We're detecting the Earth itself bobbing around in this sea of gravitational waves, which is pretty cool. Okay. Yeah, so let me, that's kind of the big picture overview. And I was just going to say I'm happy to take any questions as we go. Yeah. Oh, yeah. So this is the angular separation between pulsars in the sky. So it's not in one plane. This is a 3D distribution of pulsars, but it's the angular separation, but like in 3D, like the kind of the great circle. It's the same for all different directions. Yeah. So this is not directional at all. Pulsars in the same direction there will show the same correlation as pulsars in the same direction over here, right? It's just the angular separation between them. Makes sense? Any other questions before we move on? This is sort of like the, yeah. Yeah. Yeah, I'll show you the actual results, but when we actually plot this, right, we will have like n times n minus 1 points on this plot, right? So we have 70 pulsars, so we'll have 70 times 69 points on this plot. Okay. Yeah, so just a couple of slides to kind of put us like in context with other gravitational wave experiments. we're sensitive to very long wavelengths or very low gravitational wave frequencies. The reason for that is that we've been carrying out our experiment for a really long time. So we're analyzing 15 years of data, which means we're sensitive to 1/15-year frequencies of gravitational waves. To get an idea of what our gravitational wave strain sensitivity is, you can roughly approximate this by the average timing precision of our pulsars, which is like a couple hundred nanoseconds or so, over the time span of our data. Our most recent data set was 15 years. That's about 10 to the minus 15. So that's roughly our strain sensitivity. You can see LIGO's over here. So LIGO, of course, is sensitive to really high frequency gravitational waves and really small strains. We're not sensitive to those tiny strains. We sit up here, but we're sensitive to much, much lower frequencies. And fortunately, there are sources here with very long periods that are extremely massive, these very massive black holes. So there is a population for us to detect at 10 to the minus 15 strains, and I'll show you that soon. These are some sensitivity curves. I don't know why that's all the way up there, but this is the 2021. This is the 2031. So with time, we get more sensitive, and our peak sensitivity here moves leftward to lower and lower frequencies as our data spans get longer and longer. That's really good because we think our source populations get brighter at lower frequencies too. It's funny, on my, can anyone see, so there's like, there are actually source populations here. I'm realizing I just replaced this with this new plot, and I didn't realize the colors really don't come out on the screen. But there's a population here that looks like that, that's labeled stochastic background, and there's one that looks like this, that's labeled supermassive black hole binaries. So there's a stochastic background here that's, can you see that? Kind of, maybe? Okay, it's a little iffy. Anyway, the stochastic background population, the intensity is growing as we get to lower frequencies. And these equations here are meant to just explain that a little bit. So if you look at the gravitational wave strain from a single binary, right, of course you can estimate what that is if you know the mass of the binary, the frequency of the binary, the distance of the binary. Higher frequency individual binaries are going to have larger gravitational wave strains, but our spectrum itself is very red because there's way more sources at the lower frequencies, right, because they take more time, they spend more time at lower frequencies than they do at higher frequencies. And if you assume that these binaries are merging only due to gravitational wave emission, so the emission of gravitational waves is the only thing that's carrying energy away and causing the binaries to merge, you expect a spectral index of around 13/3. So it's quite a red spectrum. Most of the power is at very low frequencies. Yeah. Oh, yeah, I should have pointed that out. This big spike here, any guesses what that is? What frequency that is? Yeah, it's a year, so that's at 1/a year. The reason for this comes down to our pulsar timing. So when we model the times of arrival of the pulsar, we fit for the position of the pulsar, and that position basically looks like a sine wave with a period of a year in our data. So we would just fit that out in our timing data. So we're just not sensitive to those periods. You can also see a smaller spike. This is at 1/6 months for a similar reason. Okay, so I'm going to talk about our observing program now. So we need to use big radio telescopes. Pulsars are faint sources, so we need a lot of collecting area to do this experiment. For many years, our two main workhorse telescopes were the Arecibo Observatory in Puerto Rico and the Green Bank Telescope in West Virginia. Arecibo collapsed in December 2020. We stopped taking data in August 2020 before the collapse. So the current data set that I'm going to tell you about today ended the day we lost access to Arecibo. So that was a kind of natural point for us to say, you know what, let's stop the data set here on that last day of Arecibo data and analyze it. So our current data set is Green Bank and Arecibo data for the most part, and a little bit of data from the Very Large Array in New Mexico. Losing Arecibo was obviously a huge disaster. I mean, it was the most sensitive of the telescopes. It's much larger than the GBT, and we still haven't fully recouped that sensitivity loss. It's a huge disaster, of course, for the people in Puerto Rico as well. What we're doing now to kind of partially recoup that sensitivity loss is we're adding data from the CHIME telescope. in British Columbia in Canada. And we've kind of increased our observing program on the Green Bank telescope. So we're taking a lot more data with the GBT. We have a lot more time on it than we had pre-collapse. We also have a very small program using the FAST telescope in China, but it's really, really tiny. This is a 500-meter telescope in China. And it'd be great if we could get more time on it, but we only can get a very small amount of time on it. So a little bit about pulsar timing. It's just what it sounds like. We want to measure the arrival times of pulses from pulsars as accurately as possible. Here's a little cartoon that explains what we do. So at some epoch, we'll observe a particular pulsar. We might look at it for, say, a half an hour. We can't time using individual pulses. They're far too weak. So we fold the data. We'll add up every pulse on top of every other pulse at the spin period of the pulsar to come up with a very high signal-to-noise pulse profile. We cross-correlate that with a template to measure an accurate time of arrival. And then we have a timing model, right? And this model accounts for all the astrophysical things that are happening, that we know about, that are affecting those times of arrival. We'll come back, say a month later, we'll observe the same pulsar. We'll calculate another time of arrival a month later. We will compare it to our model that tells us when that pulse should have arrived, right? And then we subtract when did this pulse arrive minus when should it have arrived based on our model, and we call that a residual, right? So the residual is just the difference between the model predicted and the measured arrival time of a pulse. So if we know everything that's happening, if our model is like completely perfect, all these residuals would be 0. But of course they're not. This is what our data look like. You can go to data.nanograv.org and you can download our most recent data set. It's all public. You would get a text file. They really are still just text files, which would look like this, with a whole bunch of modified Julian dates with lots of significant digits. These are times of arrival at a particular radio frequency. So we measure over a bunch of different radio frequencies. These are errs and microseconds. So you could get times of arrival like this. You would get pulse profiles. So this is a pulse profile for one of our brightest millisecond pulsars. This is the total intensity. This is linear and circular polarization. There's lots of good emission physics in this polarization data that I don't have time to talk about. And then you get a timing model, which looks something like this. So this model has all of the deterministic things that affect the arrival times of the pulses from a pulsar. So obviously the frequency and frequency derivative, and you can see the ridiculous number of significant digits with which we can measure the spin frequency. Right ascension, declination, proper motion. These DM parameters, this dispersion measure, accounts for variations in the electron density along the line of sight to the pulsar. This pulsar is in a binary with a white dwarf star with an orbital period of about 67 days. So these are all the binary parameters. Some of them are Keplerian. Some of them are relativistic. We get this companion mass through this Shapiro delay measurement, so basically light bending around the companion. So there's all sorts of good stuff in these timing models. So much like ancillary science that we can do with these. Yes? That's okay. Good question. Yeah, so the dispersion measures change with time for a few different reasons. So basically, so this measures variations in electron density along the line of sight. So part of it is due to the pulsar moving through the galaxy. Part of this is due to the sun moving through the galaxy. Part of this is due to the Earth moving around the sun. So there's a yearly dependence there. Yeah. And actually, this is a subtlety, but since you asked, this is a timing model not from our 15-year paper, and we actually don't use dm dot and dm double dot for our most recent NANOGrav data set. We use something just called dmx because it's so complicated over this long time span of data that we just fit for a new DM on every single epoch, and we don't even try to do something reasonable like model it like this. But we're going back to something like this soon, now that we have the CHIME telescope data, because we get data every single day, and it's like too many parameters. So now we're going back to trying to make some smart, smoothly varying model like this, but that's more complicated than this thing. Any other questions about the timing or timing model?
Sorry,
No, it's good. I like questions. Yes. Not anymore. Yes. exactly. Yep. Yep. Yeah, so the pulsar was a member of a binary system. It reached the end of its main sequence lifetime, exploded, became a neutron star. Its companion was a lower mass companion, had a longer evolutionary timeline, and then when it became a red giant, that material accreted onto the neutron star, spun it up to really fast periods, and then it became a white dwarf. And so these are, so if you've heard of low mass X-ray binary systems, these are like the next stage after an LMXB. All the gas is cleared out. They're very old. These are like millions of years from that actual accretion episode. So they're very, very clean timers. So it's very well measured. It's extremely well measured. We think they're spinning down due to magnetic dipole radiation. We can model it very well as magnetic dipole radiation. So from the period and period derivative, we can infer a magnetic field for these millisecond pulsars. So the P dot, we think, is just purely due to the magnetic dipole. No like binary interaction or accretion physics comes into that at all. Does that answer your question? Yeah. Okay, cool. Okay. Yeah. So yeah, the pulsar timing bit of it is the part that I mostly work on in my own research. So like I'm part of the team that observes pulsars, creates these timing models, models sources of noise in the pulsars. So this is what our data sets have looked like over the years. This is time. We started in about 2005. And each one of these vertical lines is a different pulsar. So we have about 70 pulsars here. Our first paper was published in 2013, and we had 17 pulsars. And then with time, we keep putting out new data sets with more and more pulsars. This is really important. Our sensitivity is linearly proportional to the number of pulsars. So the more pulsars we have in the data set, the more sensitive we are to gravitational waves. So a really big part of our program, which I'm not going to talk about today at all, is searches for pulsars, actually. So like scanning the sky to try to find more millisecond pulsars to add to our array. These different colors are just different radio frequency telescope combinations. Don't worry too much about them. But you can just see that we've gradually increased the number of pulsars with time. There's some gaps in here due to telescopes being offline or problems for various reasons. You can see a few little like horizontal stripy things. But in general, we have 15 years of data on a bunch of pulsars and smaller amounts on the other pulsars in the data set. So when we actually search for gravitational waves, we have to do this cross-correlation analysis, right, to see if we can detect that Hellings-Down signature in the data. These are pulsar timing residuals. So these are the things that we cross-correlate. And I'm just plotting 3 of them for 3 different pulsars just so you can see what these look like. So these are from our 15-year data set. And again, these are the differences between the modeled and the measured times of arrival. The different colors, again, these are different backends that sit on our radio telescopes. These 2 pulsars are observed with both Arecibo and Green Bank, so they have a lot of different colors and a lot of different backends over the years. In fact, this one also has VLA data. So Guppy is Green Bank Ultimate Pulsar Processing Instrument. Puppy is Puerto Rican Ultimate Pulsar Processing Instrument. And this is Yuppie because the VLA is in a Y-shaped configuration. So, anyway, so the point is, you can see that most of these points line up with 0, right? So our models are pretty good. There's no long-term systematics that we're missing, right? I mean, over time, the root mean square of these is of the order of like 100 nanoseconds to a microsecond, something like that. So that's pretty good. You can see, though, that some points do not line up with 0. There are some departures. Are they gravitational waves? We can't tell just by looking at this, right? We need to do this correlation analysis. You can also see that there might be some noisy signatures in this data, perhaps some low frequency noise like we might expect due to these very long period gravitational waves. Oh, and the final thing I'll point out before we move on is just the scale of these residuals. So this is 1 microsecond here. And you can see for this pulsar, right, all of these residuals lie well within a microsecond, which is pretty cool for a pulsar with, millisecond period over 15 years of data. So pulsar timing works. So what will a gravitational wave look like in these residuals? Let's start with the left plot. So this top plot here shows what a stochastic background of gravitational waves would look like in pulsar timing residuals. The different colors are just for 3 different pulsars in different directions of the sky. This is before we fit for any kind of timing model. We would expect a very long timescale perturbation because the stochastic background has most of its power at very low frequencies, right? Like decades, hundreds of years, thousands of years. So a very long timescale perturbation. Once we fit our model, though, we would subtract out a lot of that into our timing parameters, right? We couldn't help it. It would get absorbed into all of our stuff, like position and the binary parameters and the period derivative. And so we get something that looks like this in the end. So when we look at our residuals, we would expect a stochastic background to really just look like noise. It will look kind of like just quasi-periodic red noise in any one pulsar. We could never tell it was a gravitational wave just by looking at one pulsar. The only way is to look for this correlated signature. Make sense? If there's a single source of gravitational waves, so say one individual supermassive black hole binary in one specific direction, then it looks something like this. So we would have basically a sine wave perturbation in our data with the period, with the orbital period. This would have the same period for all of the pulsars, right? But different amplitudes and phases depending on the angle between the Earth and the pulsar and the gravitational wave source. And unless that binary happened to have a period of a year or 6 months or 67 days, for instance, in the case of that binary pulsar, right? Like the period of something else we might fit out, it's going to look the same after we fit our timing model. It's going to persist in exactly the same way. So this kind of search is very deterministic. We basically search for a bunch of sine waves with different periods, amplitudes, and with different relations for all the pulsars corresponding to a particular gravitational wave source position. Makes sense? So we do both of these kind of searches in our data. Okay. This is just to show you, I don't have that much time to talk about all these different sources of noise, but there are other things aside from the purely deterministic timing parameters and the noisy gravitational waves. There are other things that are also noisy that we can't model perfectly. And this table lists some of those. So the pulsars aren't perfect rotators. They have some intrinsic spin noise. Their pulses aren't perfect. These single pulses jitter about in phase and amplitude, and that's a source of noise. There are some extrinsic things like variations in dispersion measure, variations in scattering. We need to rely on accurate planetary ephemeroids to correct the arrival times of the pulses to the solar system barycenter. We need to correct them to an inertial reference frame, right? It doesn't do any good to model the times as measured on Earth. And for that, we need planetary ephemeroids. Those aren't perfect. They can be a source of noise. The clocks at our observatory could have small errors or offsets. But the point of this is to show that we can discriminate all these different sources of noise because they have different properties. So this interstellar medium stuff depends on radio frequency. The rest of them don't. This pulse jitter, this is white noise. It will not be correlated in time where the rest of them are. This is the only other one, this planetary ephemeris noise, that should be correlated in space, but it won't be quadrupolar. It would be dipolar, right? It won't look like gravitational waves, right? So we can discriminate the gravitational wave background by carrying out an analysis that looks like this, right? Where we can model all these different sources of noise because they have different properties. This is what one of our noise analysis plots look like in practice. So this is the power that we measure over a bunch of different gravitational wave frequencies. This is just for this one pulsar. And this is the total power that we measure, this black line here, fitted with a power law. These orange bands are the power at a bunch of individual frequencies. And we basically break that down into individual red noise. That's this green line here. This is the noise, the red noise that's just specific to this pulsar. This red band here is the red noise that's common to all the pulsars or the gravitational waves. The reason that this is just common red noise and not gravitational waves is this is absent of any kind of like spatial correlation, right? It's just a common source of red noise with the same spectral index and amplitude in all of the pulsars. Yeah, and then we have a white noise contribution as well. The point of showing this is that we can model what we measure in a pretty simple way, right? This white noise, independent red noise, common red noise can fit the data that we measure the noise that we measure very well. Down here, these are excess noise Bayes factors. So if these were much bigger than 1, that would mean that there's excess noise that we're not modeling very well through these terms. And they're not, so we're modeling all the noise pretty well. Let me just show you one more of these. This is for a less good pulsar. So this pulsar has noise, intrinsic spin noise, this green line here. That's actually more than the common noise, right? So some of them are dominated by the gravitational wave common noise. Some of them are dominated by their intrinsic noise, depending on how good a timer they are. But we can separate out these two contributions, right? So they basically all have a spectral index and amplitude that is allowed to vary individually for each pulsar, and then one that's forced to be the same for all of the pulsars, like we'd expect due to gravitational waves. Okay, so this is the kind of noise analysis that we carry out. So let me tell you about our exciting results, and then a little bit about what they mean for supermassive black hole binaries and the universe. So I'm just going to go back in time just for a little bit of historical perspective. So our first 3 data sets are 5, 9, and 11-year data sets. So these data sets here, they all resulted in upper limits on gravitational waves. So we looked at our data. All we saw was intrinsic noise for each pulsar. We didn't see any common source of noise at all, right? So all we could do was set an upper limit on the gravitational wave background. And these upper limits, this is a probability distribution on the amplitude of the gravitational waves. They look something like this. This plot is an interesting one, though. So this is from our 11-year data set. And these dotted lines here are what we got at first when we analyzed this data set. And it looked like there was a source of common noise. It peaked at a particular gravitational wave amplitude. We were really excited. We thought we had detected gravitational waves. We didn't see the spatial correlations, but we saw this common source of noise. We were super excited. These different colors, though, are different JPL ephemerides. And so we detected this for one of these. Which one was the one first? The orange one here, right? And we were really excited because it was super significant. And then we said, okay, let's use different ephemerides and see what we get. And if we used a different ephemeris, we got a totally different answer, which was really worrying. And then we figured out the ephemerides weren't accurate enough for our purposes. They just didn't have enough accuracy. And so we had to come up with a new mechanism where we basically fit for the ephemeris at the same time as we fit for gravitational waves, and then we ended up just getting upper limits. It was kind of fun, though, because it was a trial run. Like, what would we do if we thought we detected gravitational waves? And it was also really cool because we realized that we needed better than 100-meter localization of Jupiter to correct our TOAs sufficiently accurately, which was better than JPL needs to land stuff on Jupiter. Like, they didn't even care. We were like, oh, they're going to be so upset when they find out that their ephemerides aren't that accurate. And they were like, well, that's fine for us, actually. We don't need them more accurate than that. So our next data set was our 12.5-year data set. And this is what we got for our 12.5-year data set. And so this was really exciting because we detected a significant source of common noise among all the pulsars. And we detected it whether we fixed the solar system ephemeris at the latest and greatest JPL one, which was way better because of Juno, or this French ephemeris from this other group. We also got a similar result if we used our Bayesian code that fits the ephemeris out. This was really exciting. We had a Bayes factor of over 10,000 for a common spectral process over these independent noise processes. So this means it was favored over 10,000 to 1 over independent noise. However, when we did the correlation analysis, we got something like this. So these are the binned correlations versus angular separation. This blue band here is our best fit Hellings-and-Downs curve. It doesn't look by eye like those points are really hugging that Hellings-and-Downs curve, and it also doesn't look like it statistically. This is just a visualization, by the way. When I show these plots, when we do the statistical analysis, we're looking at every single pair, right? We're looking at all the pairs. We don't actually analyze this by looking at this plot by eye, but this is just to show you kind of like what the bin correlations look like. And so we didn't detect the spatial correlation. We also didn't see other correlations, like a dipolar correlation that you'd expect if the ephemeris was wrong, a monopolar correlation like you might expect if there's just some clock error. So after the 12.5-year data set, we realized those are almost certainly gravitational waves, but we can't be sure unless we detect those spatial correlations. Other collaborations saw the same thing. This PPTA collaboration in Australia had very similar constraints on the amplitude and spectral index of this common process. The European collaboration, they saw the same common process, very similar constraints, and a combined international data set resulted in extremely similar constraints. So this was super cool. There was this same common red noise process in all of these independent data sets. And in this combined data set, it was detected with a base factor of like 10 to the 8. So super strong. So what we did with our colleagues, this is about 3.5 years ago now, a long time ago, we got together and we said, okay, our next data sets should reveal this telltale spatial correlation. Let's do this together. Instead of like racing to the finish line, let's all look at our independent data sets and then publish in a coordinated fashion. So we did that. It was a really long process and hard process, kind of bringing like everyone together in this same timeline, but it worked. And on January 29th of 2023, 18 papers simultaneously appeared on the archive, all with the results of our most recent data set analysis. So there were 4 papers on the gravitational wave background detection. NANOGrav have a bunch of other like supporting papers, EPTA and PPTA as well. So that was cool. You've already seen this result. So this is our 15-year data set, and these are the correlations that we observe. And again, this is just a visualization to guide the eye. If we look at the significance of this, the base factor for this common process is 10 to the 12, so super significant. Definitely not, intrinsic red noise to the pulsars. If we want to estimate the base factor for the spatial correlations, we do that in a bunch of different ways. Kind of the most straightforward way is to just insert phase shift into the data. So take the pulsar data, shift them with respect to each other in phase, which removes the real correlations, and then search all those phase shifted versions to see how often do we see something as significant as the thing that we saw. We do that in a Bayesian way and a frequentist way. I'm kind of running out of time to explain this in a lot of detail, but the point is that when we do all these phase shifts and compare to the signal to noise in our data, we find a significance of like 3.5 to 4 sigma. So something like a 1 in 1,000 to 1 in 10,000 chance of being just purely random. When we made this announcement in our paper, we never call it a detection. We call it evidence for, because the particle physics community wants to see 5 sigma to call something a detection. I would call it a detection because similar things, as you will see, were seen at similar significance levels in other PTA data sets. And so together, that really bolsters the detection significance. Everything checks out. So the signal behaves as you expect with the number of pulsars. As we add more pulsars and more time, we see the signal to noise increasing and increasing and increasing. So it's not just like a blip in the data. It looks as we expect if we break the data up just for Arecibo pulsars, just for Green Bank pulsars. And we did a ton of different tests like this to show that it's robust. Here's a plot of the spectrum. So these are the individual spectral posteriors for the power at different frequencies. This blue band here shows what happens if we fit a power law to the data. So this is the 1 sigma error region on a power law that we fit to those posteriors. This dotted black line here is what we expect for a population of supermassive black hole binaries in spiraling purely due to gravitational wave emission. And the basic summary is like, it's close, but not perfect, right? So it's consistent with what we expect, but you need to add in some interesting astrophysics, not just purely gravitational wave emission, but it's basically consistent with supermassive black hole binaries. It's also consistent with a bunch of other stuff. So you can explain this with gravitational waves from cosmic strings. You could explain this with gravitational waves from early universe inflation, all this exotic stuff like domain walls and so many things that I can't talk about, or I'm going to be immediately out of my element because there's like hundreds of papers from theorists on different explanations of this signal, way more than on the supermassive black hole binary explanation. And they're also consistent with this spectrum. They predict similar red spectra, so we need more time to figure out. Okay. The other pulsar timing arrays in Europe and India and in Australia detect very similar things in their data with similar amplitudes and spectra. So that's really, really nice and really reassuring. We do have some pulsars in common, but many that are not in common. So these are like kind of quasi-independent data sets, different telescopes, but some of the same pulsars. So what can we say? let me just finish up by talking a little bit about supermassive black hole binaries, which was at least my initial goal for this project, to be able to say something about galaxy mergers and evolution. So we can't say a lot yet because our signal to noise is still quite low, so we can't really do too much detailed astrophysics with the data that we have so far. But this is the general kind of like framework that we use. We have a simulation framework where we basically make fake galaxies. So we assume, for instance, some pair fraction for galaxies, some merger timescale for galaxies. We have some stellar mass function. We pick some relationship between the black hole and bulge mass, like there's all these empirical relationships between those two things. We have one model where it's just gravitational waves, one where we have other things, like an accretion disk, for instance, right? And then we create fake galaxies, we push them through this merger evolution, and then we calculate spectra, and then we basically compare those spectra with the spectra that we see to place constraints on these properties. And this is the kind of plots that we get. And again, I don't have too much time to go into this in any detail, but our constraints are also like pretty loose right now, so I think that's okay. So this shows the gravitational wave background fraction, these solid lines, that is due to black holes of like particular masses. So all this is saying is that in this like simulation framework we set up, it is the binaries with large masses, like billion solar masses, that are contributing the most to our background. It's the equal mass binaries that are contributing the most, and they're coming from redshifts of like roughly 1 or so. Okay, so these are the kinds of things that can come out of the simulation framework. This plot here shows priors on the left, these gray bands, and posteriors on the right on things like the total mass and distance and separation. We generally prefer larger masses than most models. And this plot over here shows all the different papers that have predicted where our signal should lie, like what the amplitude of our gravitational wave background should be. And these bands are the predicted signatures, and this is our measurement. So we're kind of like towards the end of most of the models. What this means is that we can explain our signal. It's not astrophysically impossible, but it does require like more massive black holes or more black holes than most models. So it's pretty interesting. Like there's some interesting astrophysics in here. Of course, another possibility is that that background is not all supermassive black holes. Maybe it's part supermassive black hole binaries and part something else, right? So one thing we'd like to do is disentangle, right? Whether we can figure out, like measure a second power law, not just one, but another one due to, say, primordial gravitational waves. They should have different spectral indices. A grad student working with me, Andrew Kaiser, published this paper couple of years ago, which showed that after about 20 years of data, we should be able to measure a second background, which has an amplitude half the primary background, and constrain the spectral index with a fractional uncertainty of about a half, or measure it with a Bayes factor of about like 100. The basic point of this is just at about the 20-year mark, we might be able to start to disentangle a second background if it's pretty bright. Another clue as to whether a background is due to supermassive black holes or one of these more exotic things is the supermassive black holes should be at some level anisotropic, right? It's a background composed of individual sources. So at some level, we expect it to not match that Hellingsen-Downs curve perfectly. It should deviate at some level, whereas these other backgrounds, like cosmic strings or primordial gravitational waves, they should be purely isotropic. And again, I don't have much time to go into this, but in about 20 years, at about the 20-year mark, these are simulations showing the power, if we have anisotropy at about the 30% level, if our power is 30% anisotropic, we should be able to discriminate that also at about the 20-year mark with a signal to noise of, say, about 3 or so. So that's pretty exciting. So in another 5 years, we'll be able to say a lot more about this background. Okay, and finally, I just want to point out, we're also searching for these continuous wave, these single sources. We haven't found any yet, obviously, but we can do things like place constraints in different directions of the sky. So in this part of the sky, where we're most sensitive, we can basically say out to about 160 megaparsecs, there are no supermassive black hole binaries with masses of about 1 billion solar masses around our most sensitive frequencies. We have a very anisotropic sensitivity because most of our pulsars, they're these red stars, lie in this part. And very few of them lie over here. So we're not very sensitive here. We're very sensitive over here. There's some galaxy clusters or sources that electromagnetically are thought to have a supermassive black hole binary in them, and unfortunately, they mostly lie in the regions where we don't have a lot of sensitivity, which is like kind of unfortunate. So we're trying to do pulsar searches to kind of fill out this part of the diagram, find more pulsars there. And by the way, this is mostly dominated by where Arecibo can see. Many of the millisecond pulsars are ones that have been found by Arecibo, so this isn't so much a real effect. A little bit of it is, but a lot of it is like selection effects. Okay. And one cool thing we can do is we can set priors based on electromagnetic observations. So this is a galaxy. It's called 3C66b. Electromagnetic observations indicate it has like a billion solar mass black hole binary in it with an orbital period of about a year. We can start off with those properties, fix them in our search, and then search a much narrower range of properties, which makes us way more sensitive. When we do that for this particular source, these are the upper limits that we get on the mass of the binary. And this is the mass from electromagnetic observations. And this is the 1 sigma region. And we're very close, actually, to being able to dip into this predicted regime and actually rule out these electromagnetically predicted masses, which is pretty cool. So this shows we might be pretty close to making a detection. So finally, what are we going to do to increase our sensitivity over the coming years? So the next 5 years are pretty exciting. We've lost Arecibo, which decreases our sensitivity a lot. We're going to recoup some of that at Green Bank. There's a wideband receiver, which covers a much larger radio frequency range than we're able to observe right now. So right now we're observing in this range here from like 700 to 900 megahertz, and in this range here from like 1100 to 1900 megahertz, and soon we're going to get this whole range. This is a pulsar signal. We're going to get way more bandwidth. That's going to increase our sensitivity a lot. We're currently adding data from this CHIME telescope in Canada. CHIME observes our pulsars every single day, whereas at Green Bank, we only get observations once a month. So you can see up here, the green and blue points are Green Bank data, and the yellow points are CHIME data. So we're going to get way more data in these residual plots. And in particular, for this dispersion measure modeling, which is a frequency-dependent effect, CHIME's going to be amazing. We're going to get much smaller error bars on these DMs because it observes at much lower radio frequencies. So this is very exciting. We're kind of still in the beginning stages of incorporating this data, so we're not real sure the exact improvement, but it's definitely going to help us. And then finally, we really need a new telescope. We need something to replace Arecibo. I'm really excited about DSA 2000. How many have heard of DSA 2000? Okay, curious if it's out there in the mainstream yet. You should hear about DSA 2000. It's going to do amazing things, not just for pulsars, but for a ton of other science cases. So this will be an array of 2,000 small dishes to be built in the Nevada desert. It's being led by a group at Caltech. We would get about a quarter of the time on it. It would have Arecibo collecting area, but be much, much more flexible. And if we really want to dip into these single source populations, this gray band is a simulated population of single supermassive black hole binaries. And this is without DSA 2000, and these lines are with it. We really need something with a lot more sensitivity. So this is after 10 years of observing with DSA 2000. We should detect dozens of individual supermassive black hole binaries. And finally, we need to grow the pulsar timing array. And again, DSA 2000, this is a simulated plot of all the pulsars that will be discovered with DSA 2000. It might detect, thousands of millisecond pulsars. And we should be able to time hundreds of them with excellent precision. So this is going to be really, really important. And finally, I haven't talked much about the international collaborations, but we're working on a data set that's a combined data set of all the radio telescopes in the world doing this. It's called DR3 because it'll be our third combined data set. And it is combining data from, all of these telescopes right now, but the CPTA. We haven't gotten them on board yet, but we hope to get them on board. But all these other telescopes will be part of this combined data set. And it's going to have 115 pulsars. And these are sensitivity curves for single sources. And these are simulated populations of single sources. And in 2025, when we have this combined data set, we expect possibly a few of these single sources to sit above our sensitivity. And this in particular is this 3C66b source that I talked about before. So this is really exciting. We could be very close to detecting a single source. And I'll just leave this pretty picture up here and stop there.
Wonderful talk. I kind of work on stuff related to NANOGrav, specifically about that, like constraining the function binaries.
Cool.
But I'm also thinking a lot about like kind of how we distinguish
Mm-hmm.
the
Yeah.
singular binaries. And does it have to do really with the because I feel like that's really the science how to big difference between those two things. I was looking at like the recent NANOGrav papers. I believe there wasn't
There's
anisotropy.
no anisotropy detected yet.
Did we expect that based on our activity level?
No. Yeah, that's a great question. So, yeah, so I didn't show the results for our anisotropy analysis because they're pretty boring. Basically, they just say there's no anisotropy yet. So right now, it's completely consistent with an isotropic source population. But that's also completely expected. So given 90-some% of realizations of supermassive black hole binaries in the universe, and given our sensitivity, it should look isotropic right now. And another 5 or 10 years, then we should start to detect anisotropy for most realistic supermassive black hole binary populations. So yeah, so right now it's just like not informative really between those models. Yeah, good question though. Yeah. Yeah. It's a good question. So right now we are using Gaussian processes. So we're just applying like Gaussian process regression, and we're not. We're just pretending that like we don't care about the astrophysics at all. So we're just applying Gaussian processes, trying to fit these frequency-dependent variations out. So that's one approach to the timing. I also have a grad student actually whose project is modeling those DM variations astrophysically, because like the Gaussian processes are one thing, but they better make sense astrophysically. So she's modeling these long-term time series with like a linear term due to the pulsar and Earth distance changing, an annual term like with a period of 1 year due to the Earth moving around the sun, cusps due to the solar wind for those pulsars that are line of sight passes close to the sun, some stochastic variation. So there's a couple of different approaches. There's like one that's really based in the astrophysics we know that's happening, and then this Gaussian process thing. I think for the fitting, the Gaussian process thing will be what we'll do. It's the only thing that'll work for almost every pulsar. Yeah, but there's a lot of interesting science, right? So I'm hoping from her project, we'll be able to constrain really well like what the kind of clump size of stuff in the interstellar medium is, what the relevant velocities are, or at least the ones we don't know already. Yeah, it's an interesting question. Machine learning's like so popular that everyone's always like, why don't you apply machine learning to the data? For the timing model bit, there's not much that machine learning can do because we really are searching for like completely deterministic signals. Like we know exactly what they look like. And so it's very simple. We do least squares fitting on the data. And I don't think there's really a role in the timing model generation for deep learning, but I'm also not an expert. And if you are and you have ideas, I'd like to hear them. I think there might be more of a room for deep learning maybe in the gravitational wave searches, like, trying to model the regime between a single source and a stochastic background where you might have some complicated superpositions of sources. Like maybe, right? Like maybe you could have a deep learning model that could try to tease stuff like that out, but I really haven't thought much about that either.
One last question.
We are. Yeah, they're not that interesting. So like Planet 9, for instance, we're not sensitive enough to say whether or not that exists. Like Jupiter, we're really sensitive to because it's very massive, and its orbital period was really close to the 11-year time span of our data set, so it was like a perfect storm. But yeah, we can place constraints for sure. In fact, I have a postdoc, his name is Loki Day, and he's leading a paper on exactly this, like what kind of constraints we can place on interstellar objects and asteroids. They're not super interesting yet, but for sure, I mean, they all have gravitational perturbations, and if they're not incorporated in the ephemeris, they're going to be a source of error for sure. Yeah.